We are joined by Patrick Gorski of the Wisconsin DNR. And Patrick is a research scientist with the DNR. He studies a variety of water contaminants, but one of his main focuses lately has been PFAS. And so he's going to tell us all about PFAS. He's going to tell them what PFAS stands for, and he's going to make sure that by the time everyone leaves today, everyone can successfully pronounce what PFAS stands for. It's a very long, complicated word, and so everyone's going to have a lot of fun with that. And I'm really excited for the talk today here. So what I'm going to do now, I'm going to stop sharing my screen, Patrick, so that you can share yours. And as we go, if anyone has any questions, just pop them in the chat, and we will answer questions at the end of the presentation.
Awesome. Thanks, Emily. Hopefully, let me see. Share sound, share. All right. Am I in presentation mode? Just checking.
You are. It looks and sounds great.
Okay, good. Excellent. So I'm going to be talking about, as Emily said, PFAS in Wisconsin surface waters. So I'm going to mainly focus on surface waters. I know PFAS, there's a lot of interest in PFAS in drinking water and other media, but I work in the Bureau of Water Quality. So what we study is, lakes and streams, and so forth, what probably a lot of you monitor out there. So that's the general area that I'm going to be focusing this on. So in today's talk, I'll, as Emily said, I'll hopefully answer what is PFAS, where does it come from? Also, I'll give you an overview of some of our statewide surface water results. And PFAS, like a lot of contaminants, it's, the devil's in the details. So I would like to put, these concentrations in context, because often when you're analyzing for PFAS, you'll find them, but the concentrations matter. Also, what we know about PFAS in fish as related to surface water. I work a lot with the fisheries folks here at the DNR and the advisories that come out, and there's a correlation, and I'll talk about that. I'll give you some an overview of the Lake Monona, of a research project on Lake Monona, where I'm studying PFAS. Also, I'll give you some examples of different PFAS sampling techniques. I know a lot of you are out there in the field sampling, so this may be of interest to you. These aren't the average techniques that you may be using, but I thought it might be fun to see some of those and other projects and monitoring that we've been doing at the DNR. So I'm going to delve into a little bit of chemistry, because I think it's a good idea to get a base of knowledge of what PFAS is. It's in the news a lot, and I know it's in the governor's budget and so forth. There's stories daily that are coming out in Wisconsin or worldwide. So PFAS is actually, it's an acronym, and it's actually a plural acronym. So it's per and polyfluorinated alkyl substances. So these are organic compounds, and these are man-made. There's no such thing as a naturally occurring PFAS. These are all man-made organic compounds. There's over 5,000. There's probably over 6,000 or 7,000. It increases almost daily by people discovering new ones. But the important thing to remember is they've only been around since about the 1940s. So around World War II, is when they are discovered and first manufactured. So before that time, they didn't exist naturally, and it's something that organic chemists created. One of the first compounds that was made was Teflon, which I'm sure you are all familiar with. So I want to get down into what it is composed of chemically. So it's a carbon chain. So there's a chain of carbon atoms, and they're attached with fluorine. And if they're fully fluorinated or not depends if they're per or poly. Fluorinated alkyl substances are fully fluorinated, so that carbon bond is completely saturated. And that bond between the carbon and fluorine is one of the most difficult to break in nature. And that's why they get the name the forever chemical, because naturally that's very, very difficult to break or almost impossible. So that's where that idea comes from, where you hear them called the forever chemical. They're composed of this fluorinated carbon chain, which is considered a tail. And then at the other end, there's this functional group, which we call the head. And then that chain length can vary from 4 to 12 carbons. So there's really short ones and really, long ones up to 12 carbons. And here's an example of PFOA. This is one of the compounds that gets a lot of attention, and there's in the lower right here is the caricature of, let me get my little laser pointer going, caricature of the carbon fluorine tail, and then the functional head in the on the right side there. These are carboxylic acids. So this head right here is basically carbon dioxide. So right at this point here, this is a carbon, and then 2 oxygens coming off at. So, and also it's important to keep in mind, PFOA, the O in PFOA is octa, which stands for 8 carbons. Similarly, there's a sulfonic acid, which is PFOA or PFAS, PFOS. And that's another 8 carbon. The O is again octa, so PFOS. There's 8 carbons. So in this, for this example, instead of a carbon here, this would be a sulfur group. And that changes the functionality of the compound. The main 2 compounds I might be talking today about are PFOA and PFAS. There's a lot of other ones out there, as I mentioned. Usually when analyzing them, we get back like about 33 that we've been routinely measuring. But these are the 2 that have been used or studied most widely because there's the most toxicity data on PFOA and PFAS. Also, the surface water standards in Wisconsin have been established for these 2 specific compounds. Also, these are the ones most referred to in drinking water standards and so forth. So I'm mainly going to focus on these 2 right now. Often people interchangeably use PFOS, PFAS as FAS. When they're talking about one, they mean the other, so be careful there. PFOS is the one that has been shown to bioaccumulate in food chains and in fish. So PFOS is the one that's usually measured in fish tissue, and that's what fish tissue advisories are based on, that concentration of PFOS in fish tissue. There's some other structural properties that make this important and why eventually it's used in, or was used in manufacturing. The carbon chain repels water and oils, and the head is very polar and it's attracted to water. So it really forms films at boundaries between air and water. So one is sticky and one is hydrophobic as far as water is concerned. And then, so it's excellent at water and oil repelling properties. And this is what was attractive to organic chemists when they developed it. So it became popular in very many applications throughout industry. One common use was Scotchgard, a 3M product. And of course, you put this on some sort of fabric and it will repel water or anything that you spill. Teflon, as I mentioned, is another application. It was widely used in food wrappers. These are the ones that are more papery when you have that film. This is often, back in the day, it used to be wax, and then it became PFAS. Pizza boxes, they're phasing these out as we speak. Also, chrome plating, some personal care products or, uses for let's say lipstick or cosmetics as well. It is in some types of dental floss. Also electronics, coatings. Also here I have a 55-gallon drum. If you don't want your drums to rust and fall apart, often it was used on the liner of 55-gallon drums. Also, if you remember back in the day, or at least when I was growing up, everybody was worried about falling asleep with a cigarette on the sofa and causing, your sofa or your chair to catch fire, or curtains. It was often used in curtains and carpeting to avoid them catching on fire. So it's a flame retardant. Also, not only as a flame retardant, but it also is really good at smothering really nasty fires. So you have what's called, the acronym is AFFF. It's aqueous film forming foam. That's a tongue twister, but it's used to basically smother fires. So if you have a really bad like gas fire, or it's really common to have these compounds in firefighting products at airports, because if you have as we know, if you have a large airliner full of air fuel, you basically have a bomb. And you want to put that out as quickly and as efficiently as possible. So this is really good at smothering flames. Also, in this picture, you can kind of see if you use it becomes a problem if you're using this near water. So some notes I want to throw in here about some analyses about the analytical considerations that most people don't know about. It uses very advanced and expensive instrumentation, a thing called a LC-MS. These are expensive instruments. They've been around for a couple decades, but we recently established methods. So that's why you're starting for the analysis of PFAS. That's why you're hearing about it. But it's not basically like, some sort of simple tabletop instrument that you could use. This is, pretty expensive. It requires high-end training. It's also very sensitive. That's also why we're seeing PFAS talked about more, because we can actually measure their concentrations. The water values are often measured in nanograms per liter or parts per trillion. So this is a very, very low level. Also, that because they're at their really low level, that's often easily contaminated. So you have to have special protocols when collecting the samples, and also analysis if you have Teflon or anything coated with PFAS, obviously, during the analytical process that would contaminate. We usually measure about 33 compounds. I said we're going to be talking about 2. So you may detect some of these other compounds as well. I'm not going to get into that. Also, it's time consuming. There's prep, analysis, data reduction. Once you get everything, you have to confirm all the compounds and QA/QC. But when you're talking about time, this means labor. So it's not something that you just sort of dilute and shoot into an instrument. This is a pretty involved process, and it uses certified methods. All the labs that analyze PFAS in Wisconsin are certified. We use the State Lab of Hygiene. There's other private labs, but the EPA has come up with a certified method. Because of that, if you send a sample to a private lab, a public lab that's certified, you'll get the same results regardless of where you send it. So that's very important. Because of that, all of what I mentioned, it's very expensive. If we're in a room right now, I would ask people, well, how much do you think it costs? I've done this with some monitoring groups, or like, various lake monitoring entities, and as well, $20, $30. No, because of all this, it's $500 a sample. So keep that in mind when I'm showing you the results. It's $500. Let's just for one water sample. Let's say if you want to analyze a fish, it's also $500. Often when we do fish advisories for one species, we like to analyze at least 10 different individuals for one species. If you have multiple species, anyway, this adds up if you want to look at a lake fully. So everything I'm going to be talking about, for the most part, is publicly available. We've established this PFAS interactive data viewer. If you go to this website, I was going to click on this, but I don't want to screw up the website. It'll look like this. And we have all the PFAS results for different matrices, for lack of a better word. For example, any fish advisories, they're in this brown color here. There's some spill or investigation sites, which are the squares. Municipal drinking water in green or aqua are the circles. What I'll be talking about and focusing on our surface water, which are the diamonds, the pink and the blue here. And if you go here, you can scroll in and out. You can zoom in on the whatever point you're interested. You can click on it and you'll see the actual concentrations. So we started doing this in about 2019. That's when we started fully investigating PFAS, and we had an influx of funding at that time, got a little more money to do various things. And actually, I was hired in 2020 because it really, it takes someone to focus on this and really look at it. You can't just do this on the side. So we now have more dedicated staff to just focus on PFAS. My goal here is to start showing you a little bit of what we've seen statewide to give you a flavor of what we've been doing and concentrations, because like I said, you have to put this in perspective and see, what's high, what's low, and to give you a better idea. So the first data set that we did was the long-term trends rivers that we analyzed. These are 43 rivers throughout the state. They cover the majority of the state, and they've been specifically chosen to represent the major geographic regions of the state and the watersheds. I'm not expecting you to see the actual numbers here, but you can see the locations and the different colors. I'll get into that. Often you hear in the news about high levels or really contaminated areas. That's what usually makes the press, but a lot of times there's good news, and some of that is people don't talk about a lot of the non-detects and the areas where it's not found. So for PFAS and PFOA, for PFAS, like 37% of these sites were non-detectable and 19% were non-detectable for PFOA. So a lot of low levels out there in these rivers. And when detectable, these were pretty low concentrations. PFOS was less than 5 nanograms per liter. 5 was the highest. So average of about 1.4 nanograms per liter, and for PFOA, 2.2. So these are, I'll show you some higher concentrations, but keep these in mind. These are relatively low. I've circled some red areas where regionally they tended to be a little higher. So that's the Mississippi River, the Wisconsin, and the South eastern Wisconsin. Those were higher. Definitely the north western part of the state were lower or non-detectable up near, once you get near Lake Superior. Now I want to highlight, so once we start getting an idea of what's out there, keep in mind also what we want to do is figure out what are sort of these background or ambient concentrations in areas away from, major cities or industry and so forth, and then contrast those with more urban areas and areas that may have input from, for example, wastewater treatment plants or industries or just public usage or runoff. Anyway, we've started looking at river systems to figure out what's going on in PFAS for different river systems. One area here is the Wisconsin River. We've been collecting routine samples the past couple years just to get view orientated. These are the concentrations on the left, and on the bottom, on the left side is the north end of the Wisconsin River, and the far south on the right, PFOA is in blue, PFOS in orange. And as you can see, also I want to give you the concentrations here. So we have established surface water standards for PFOS and PFOA. PFOS is here at 8 nanograms per liter. You can see on the left axis. PFOA is much higher. The surface water standard in surface water is 95, so it's off the chart here, nanogram per liter. There are certain parts of the state that use surface water as drinking water. If it is used as surface water, or I'm sorry, as drinking water, then that standard is 20 nanograms per liter. There's no municipality that uses the Wisconsin River as drinking water. Just keep that in mind. But let's look more at the sites here. So far northern part of the Wisconsin River, rainbow flowage, non-detect. But as you get to Rhinelander, you see just south of Rhinelander, there's a road, Hat Rapids. You see an increase of PFOA. And this is less than 95. It increases there and remains somewhat elevated throughout the river system, but PFOS is generally low, less than 8. So it's not exceeding the surface water standard in any of these sites. But we have been noticing fish advisories on some of these impoundments. You probably heard about it in the news. So we're going back and we're going to be sampling these a little more and trying to figure out what's going on in some of these areas. Like, for example, I think the Stevens Point flowage just recently got in a fish advisories. So we're working hand in hand with fisheries to go back and figure out what's going on. We're also going to be going back and sampling the Rylander area this upcoming field season to go back and figure out exactly what's happening here. Another river system which is different, contrasting, is the Yahara chain, which is in the Madison area. Of course, again, we have on the left side, here's the 8 for PFOS. And then also one area that you may be, about, or has been in the news, is Starkweather Creek, which flows from the airport into Lake Monona. So that's where that comes in about here. Monona Bay is part of Monona. But here, you can see these all of them are a lot, at least for PFOA. The blue is a lot lower in this system, but is contrasted with the higher PFOS in the orange. And you can see at Lake Monona, it's much higher. And remains elevated all the way through the system. This goes through all the way to the Rock River. So you have the different lakes like Monona, Wabeesa, Kaganza, and so forth. I have a couple areas to contrast this with. Actually, Lake Mendota, which is upstream, is very, very low. And Devil's Lake I have here, which is we would like to think, completely in the middle of nowhere. There's no industry and so forth. This would be a good example of what we could anticipate for like a background or a more pristine site. That's on the far left. But as you can see, Monona and downstream is much higher. Yeah, in Monona itself, we've sampled multiple times. It's above 8, and not surprisingly, there's fish consumption advisories throughout the Yahara chain. Obviously, because the PFOS is somewhat elevated as it goes downstream. Here's a snapshot. I thought it would be good to see some of these average concentrations all in one graph. Far at the left, this is Starkweather Creek, the west branch. This is the branch that comes from the airport. Here I flip colors on you a little bit. So PFOS is gray, PFOA in white or clear or empty or whatever. But as you can see, these average concentrations at the west branch for PFAS are well triple digits, above 150 nanograms per liter. Silver Creek, which is comes off of Fort McCoy, up near the La Crosse River. This is also somewhat high, above 20. These are double digits for PFAS. There's also a fish advisory on Silver Creek for the trout up there. I showed you Lake Monona and downstream. Here's a comparison. But then also the Wisconsin River, the Mississippi River is relatively low. The Menominee River is very low as well. The Menominee is between Wisconsin and Michigan, between Marinette and Menominee, Michigan. There's some PFAS in the groundwater up there, but it is, as far as we can tell, not going into the Menominee River. So that's very low. And here's all those long-term trends rivers as well. So as you can see, a lot of the streams and rivers in the state are relatively low, but we do have some definitely high values that we're looking into. How that relates to fish is important thing to keep in mind. This is our state toxicologist, Megan Williams, I have her name on the bottom there, pulled together Wisconsin and Minnesota data, and we looked at water data for PFOS and fish data, fish concentrations for PFOS, and I've plotted them here. The water's on the bottom, the fish concentrations are on the right axis, and then also these horizontal dots are the different consumption advisories. The first one at greater than 10 is 1 meal per week. Above 200 is where you get into the do not eat range. So if you look on the bottom here, you can see the different water concentrations, and our surface water standards is about 8. Often when you get definitely below 1 nanogram per liter, there is often not advisories. Between 1 and 10, you may or may not have advisories. Below 5, usually you don't, but then you start to get them. This is probably the area where we're seeing like the Wisconsin River, some of these middle concentrations of water, and then those are often correlated with fish. Or just in general, let me step back a little bit. Just in general, the water and the fish are correlated. But definitely if you get into the double or triple digits for the water concentrations, that's when you also see, triple digits in the fish concentration. And that's where you get above the second tier advisory or the do not eat category. If you're above 100 nanograms per liter in the water, chances are you're probably going to get into this do not eat or a more restrictive fish concentration in the fish. We're starting to look a little more at fish. We're seeing that it's highly variable, and that's what this graph is looking at. I used to study mercury, and with mercury concentrations, the farther you moved up the food chain, or as the fish became more fish eating, the higher fish on the food chain that ate exclusively fish, their piscivores, tended to be higher in mercury. We're not always seeing that with PFAS in fish. Here we have different colors to represent the different feeding guilds. In blue are insectivores, the orange is omnivores, and the green is top carnivores. If this was a mercury graph, you'd probably see a really strong positive correlation, but here it's highly variable and it really depends on the species. That's why we've been seeing things like advisories in smelt or other fish that are kind of lower on the food chain. For some reason, crappies can be higher, white bass can be higher, but we haven't necessarily seen that in all systems. So we don't have a hard, fast rule for what's going on with the species of fish, but we do see that correlation with the water. So in conclusion of this part of the talk, the majority of the statewide PFAS concentrations are usually very low. Exception are those high sites that we've been following up on and looking at. They're usually associated with some contamination of some sort. And most sites have the PFOS and PFOA lower than our surface water standards. So we've been going back this next year, this year and the following next year, to resolve some of these changes in PFAS where the fish advisories are noticed. We've seen that correlation between water and fish, but it's not necessarily related to the feeding habits or necessarily species. So I'm going to talk a little bit about a project on Lake Monona that I've been doing and dive down a little bit in how PFAS is distributed and partitioned within water to figure out and tease apart and hopefully get at some of these nuances of how that may determine PFAS accumulation or transportation in water systems. So why Lake Monona? As I mentioned, Starkweather Creek is one of the highest PFAS concentrations in Wisconsin, average, almost up to 200 nanogram per liter range, and it's consistently high on the surface water. It's between 8 and 10. There's the fish consumption advisory, Monona downstream, and then also this is near the lab, the central office, and southern district, the state lab of the DNR, so we can get a lot of people. We can work together, and it's very convenient to work on this right here. And then also, I got the funding that we got to look at this, and if you're a volunteer monitoring or into volunteer monitoring, this might be important. So how does this relate to monitoring? Well, the way that we take a sample is to basically take or monitor for PFAS is take a grab sample. So what we do is you take an empty bottle, you dip it below the water, you open it underwater, you let it fill up, you cap it underwater, and you bring it above, because you want to avoid that potential film or that that PFAS may have at the water. So that's how we take all the samples statewide. So it's a 6-inch below the surface grab sample, and that's a total sample that takes, that's not filtered, it's not changed in anywhere, manipulated. But we've only taken that type of sample. But what happens if we take it horizontal or vertically farther down? Especially if I'll get into lake stratification, it does that vary. Also, like I said, that's a total sample. How is the PFAS distributed to particles, or is it dissolved? Is it floating around basically in the water? And then how does this get into and is distributed to different non-sport fish? Fish-wise, the only thing we sample are sport fish, fish that people will eat, let's say like a panfish or larger, or like a walleye, bass, and so forth. So we want to look at some of these other components to figure out how PFAS is distributing throughout the ecosystem and in the food chain. So we want to sample sediments, zooplankton, algae. I've listed a whole bunch of other components here. So I'll delve a little bit more into wondering how PFAS is distributed, or the question I'm getting at here. So like I said, currently all water samples are taken at 6 inches below the water surface. So how does it distribute vertically in the water column? I'm not sure if you're familiar with hypolimnions and stratifications, or actually thermoclines is what people often talk about, but this is what it looks like graphically. For this type of graph, this is the surface of the lake. So imagine a boat up here. This is 0. As you go deeper in the lake, the numbers increase. And then here on the y-axis is the concentrations. The farther you go to the right, the more they increase. So that's the surface. That's the bottom of the lake. But when a lake becomes stratified in the summer, if there's a lot of it gets warm, it gets heated up. As you may or may not know, the coldest, here we have red for temperature. Some of the coldest water is at the bottom of the lake, but then the warmest water is at the top of the lake. And then you have this gradation called the thermocline. If you swam in a lake and you dangled your feet below or dove down, sometimes you feel that cold water in summer. That's what's going on here. But also, if there's a lot of productivity in the lake, as things like algae falls and down to the bottom, and other things start decomposing, this uses up the oxygen and it gets anoxic. And so you have a chemocline potentially here. You have the also things building up is like iron, sulfide, and manganese. As you go farther in the lake, the concentrations of those, also total phosphorus, becomes dissolved and may build up in the bottom of the lake as well as you get this decomposition going on. But so how does will PFAS do this? No one's really actually looked at that. So that's part of my goal. And if you also look at just the surface of the lake and drill down on that area, that the film forming characteristics of PFAS, because of that, you can also get concentrations in what they call the surface microlayer, which is just at that interface between the water and air. That's the surface microlayer boundary. And then also, if you have turbulent environment like here, you can get foam forming, much like soap, as you churn up the water, except this is this will be concentrated in PFAS. You can have foam, or I mean, you may have foam, but you may or may not have PFAS in the foam. You need PFAS in the water to create PFAS high concentrated foam. So you may or may not have PFAS in the foam. But when you do, it can get concentrated. And here's some examples of the boat launch in Monona. Here are some examples of foam that we collected. This is Lake Nakabe near Crivets in northeastern Wisconsin. These are 1 gallon baggies, Ziploc bags of foam. So it was pretty prevalent. So we collected foam here, we collected water. I'm kind of going off a little bit on a tangent here. This isn't Lake Monona. The DNR ourselves, we don't collect or we don't analyze foam. We've been working with UW-Madison and they have a project and funding to analyze the foam, and they're looking at this interesting characteristic of what foam does. We're working with a lab. The professor is Christy Remenkoll, and her postdoc is Summer Sherman. And they have this nice YouTube video of what they're doing, and I'll quickly play this. So I'll sit back and hopefully you can hear this. If my cursor is not. Sorry, maybe that. Oh, wait, okay. All right.
I packed a foam kit and a surface microlayer kit in my car, so I always have one with me.
My name is Summer Sherman, and I am a postdoctoral research associate in Christy Remenkoll's group. We are basically asking people to report foam sightings to us. Foam is super intermittent. It can be there for 10 minutes, or it could be there for 2 days. Let's say you have a very small amount of, let's say, PFAS within the water. In the foam, when it's concentrated, it could actually be a lot of PFAS. PFAS, it's an acronym. It means per and polyfluoroalkyl substances. These compounds are everywhere. They are within your non-stick cooking pans, they're in your rain jackets, in our drinking water, they're in our blood, and they've been found to cause negative health side effects with super high concentrations. There's actually not a lot of data on PFAS in foam, so this type of research is really necessary. Per site, basically what we are trying to look at is the concentration of PFAS in the water column, the surface microlayer, and the foam. So we want to see the differences between all three of those different types of water. The other thing that we will be looking at is basic water chemistry. So we also want to understand how this PFAS partitioning might also change as a function of the water chemistry. Being able to actually work with the community is actually a pretty cool experience. You get to work with people who really care. So a lot of them are in these water monitoring groups, and they ask me what more can they do. I feel like there has been, throughout our history, such a barrier between the community and science. Since these people actually care, if I tell them the information, let's say there is a problem, they care, they're gonna push policymakers to actually make a difference. They really do want to see their lakes clean.
Okay. Yeah. So Summer is the one collecting foam and analyzing it. And we're working with her on a regular basis. I thought it might be, I'll show a couple of videos of other types of sampling. I thought this might be interesting, how to collect surface microlayer samples. And this is also in another postdoc in the lab showing me. For some reason, if I have the laser pointer on, this doesn't work. Okay.
Takes a long time.
So what you do is you basically dip a glass plate into the water, and the whatever is bound to or on the surface microlayer will adhere to the glass.
Halfway.
And then you tilt the glass, and then that will run off into the bottle. It sounds like it would be a lot more complicated, but this is how you sample surface microlayer. Sample the surface microlayer. So we'll analyze also this for PFAS. So I thought that might be interesting. And then also, how do you sample water vertically in the water column? What we used is this. It's called a GoFlow Niskin by the Frontier Geosciences. There's a closure at the top and the bottom. There's a rubber seal, ball and gasket here. What you do is you drop it is closed. We had this cleaned for PFAS as well, but it's closed when you drop it into the water. When it gets to the right depth, you open it up. So the air will escape, it'll capture the water. Then you send a messenger down, you close it and you bring it up. These are often used in oceanic sampling. Here you have an array of them and they'll fire off at different depths. And you can collect a sample here. Here's a video of us doing this on Lake Monona this past summer. I thought this might be interesting.
You good?
All right, yeah, looks good. All right.
So they're lowering it to, I think it was 6 meters. And remember, there's air inside of it and the vessel is closed right now.
All right, so we're,
Are you at 6?
okay, so Jim's gonna trip the trigger. All right, so that'll open the go flow. Now we should wait for bubbles because it's empty. All right, so that was the air inside of the go flow. Now Kim's gonna drop the messenger to close the go flow. Awesome, so now the go flow is closed and bringing it to the surface.
All right, so, and then you, there's a spigot on the side of that you open up and you can actually take your sample. So it's a little different than some other samplers that you might have used. But so these are the results that we got from that sampling. Once again, this is on the left, that's the depth from the surface. So 0 is the surface water interface. And you get deeper as you go down. PFAS or PFOA and PFOS are in gray and black. And as you can see, they're basically similar from top to bottom, as opposed to, let's say, like the dissolved oxygen, which completely is gone. It's completely anoxic below 8 meters. Here you have the thermocline. So you see the gradients for oxygen temperature here. Also, it's very well stratified, big thermocline. You also see chlorophyll A, total suspended solids that are stratified, but not PFAS. So it was anoxic, and even there was an algae bloom, and there's a lot of total suspended solids up there. But PFAS appear to be basically not stratified, or we might say it's mixed, and they're both within 1 or 2 nanograms per liter top to bottom. So PFAS does not stratify or follow other chemistry parameters there. Also, I want to look, maybe I'll go through this pretty quick. I mentioned, is it PFAS bound or dissolved? Where is it partitioning to these samples? And does that vary with PFAS? And this is important for bioaccumulation and algae. I have some caricatures of algae on the top, or sediments or particles if they settle out. But just really quickly here, we measured 13 different types of compounds, but the most prevalent one was PFOS, which was 22%. PFOA was 7.4. So this was not bound to particles. This was just free, basically, in the water, for lack of a better word. Whereas what was bound to the particles, the only PFAS that we measured was PFOS. That was 100% of the sample was PFOS that was bound. So no other PFAS we found bound to particles. So if we actually look at this on a mass balance basis, like the total nanograms, most PFAS, especially PFOS, is in this dissolved phase and is not bound to particles. And that may help explain, for example, the Monona, where we're seeing it farther down the the river, or the Yarra chain, it's still in the aqueous phase. It's going along with the water. It's not partitioning out or settling. But that 19% might be important, because that's what's getting into the algae potentially, or the particles maybe going into the settling out in the sediments, or going in the food chain. And then I think I went over this already. So we don't have a lot of information on these other aquatic components. This is what it looks like when we went getting zooplankton. I was working with a graduate student, Grace Armstrong. At the bottom of the zooplankton mesh is a 63 micron mesh here, and we partitioned it between algae and zooplankton. That's how we got those samples. I still don't have results for that. We looked at other biota. Here you can see what this is. 2 days of picking biota like this gets. We need at least like about a gram or so. But it was really time intensive. We got a lot of small fish, young of the year, bluegills, walleyes. We have cladophora, we have macrophytes. We're still getting samples there. We have another project looking at Phragmites, if you're familiar with Phragmites, which is an invasive plant. But we have some Phragmites growing in a settling pond that is known to be high in PFAS. So we're looking at PFAS and the distribution of the plant. And just like last weekend, we're also looking at sediments. Here's the crew. Here's Summer Sherman with us. She's studying PFAS in ice. We drilled a hole in the ice. You put down this core tube. You collect the core from the lake. You pull it up. I don't have a lot of details. This is the space in between the rubber stopper here, and this is the sediment water interface. And then what you at the top of the core, you can see it's very flocculent. There's high concentration of water in those sediments. Once you get farther down core, you get this push-up pop effect where you can slice the sediments and look at them. And we'll be sectioning this, or we did, and we're looking to about 1900, because that's before when PFAS was used. So I'll end it there and stop for questions. So thanks a lot.
Thanks, Pat. It was super interesting to learn about all the different types of PFAS and how you're sampling them at DNR. And we do have a lot of questions.
Okay.
The first one that I want to start with is that someone asked, why are we concerned with the levels of PFAS or PFOS? Katie put a really nice diagram in the chat talking about the effects of PFAS on the human body, but do you want to just cover that real quick?
Well, why are we concerned? Well, I mean, it's been at high concentrations. We know it's a health hazard. It causes cancer. It will has effects on your hormones. So there's definite toxicology or health concerns with high concentration. You can get it from drinking the water or eating, fish that are in high levels. When I say drinking water, hopefully not a lot of people are just drinking surface water, but there are areas of the state that have high levels of PFAS in the aquifer, and it's coming up through their wells. So is that?
I think that answers that question. Yeah.
Okay.
Yeah, the next question we have, someone's wondering, we have a lot of volunteers in the audience and they're looking to get involved here a little bit. Someone's wondering if there's grant money available to test surface waters in lakes or inflow streams to the lakes.
Good question. I don't know if there is. I don't if the various lake associations, if they can get money for PFAS analysis or not. I don't know. I mean, you probably know the WAVE budget more than I do. I would hope that you could do that. I mean, like I mentioned, it's not cheap. It's, like one sample would be $500, but it would be important information. Obviously, the DNR can't do it. I mean, everybody, people know that Minnesota's lake of 10,000. Wisconsin has 15,000 lakes. So we can't sample everything. We're trying to do what we can each year. Hopefully there might be, I know that the governor is going to be announcing his budget this year, and there's some PFAS funding in that. Hopefully if that doesn't get cut, some of that, I don't know exactly what's earmarked, but hopefully that would be available. But don't quote me on that. I don't know what's in the budget, but.
Okay, our next question is, are PFAS and PFOA not able to be detected by traditional methods? And is that why we didn't find it decades ago at other sites?
Oh, yeah, exactly. So the technology is advanced where now we can detect it. We can't, before, let's say about 20 years ago or so, we didn't have the technology and the methods to do this. So now that we have the methods refined, now we can detect it, especially at those really low concentrations. As the technology advances, the limit of detection decreases, so it's more and more sensitive. So yes, that's why we're seeing it. And we're more confident in those measurements as well. And that's another thing too. You need this type of instrumentation to analyze it. I've seen some one-off advertisements for really cheap analyses that don't use this. I don't think I would trust that. You definitely need a LC MSMS. The MS is a mass spec. That's what you need to detect these low concentrations. That's a detector.
Thank you. Is there anything that's being done to clean up PFAS or PFOS?
There's different levels of technology that you can use. So the answer is yes. You basically can use, there's different steps to this. You can remove it, you can concentrate it, and you can destroy it. And I think we're at the point where we know how to remove it. Definitely. There's this stuff called granular activated carbon. So basically it's like a carbon, if you're familiar with fish tanks where you have the carbon filter or the charcoal filter, often they use things pretty much like charcoal. That'll absorb PFAS to the carbon, the activated carbon, and you can remove it. The next level is concentrating it more, so you can get a more effective way of concentrating it. The research right now is on destroying it, because if you just remove it and concentrate it and put it in a landfill or somewhere else, you're just moving the problem. Ideally, we want to get to the point where destroying it, we can destroy it. So there's a lot of new technologies. That's where a lot of the research is happening right now. But I've talked to a few people that the problem that you want to get at is you don't want to have it get out in the environment, because once it's widespread in the environment, it's really difficult. Then you have a non-point issue that you're dealing with. If you can get to the source, or it's a very localized, it's easier to deal with. Once it's widespread, obviously it's harder to remediate.
Okay, next question is, since we're just starting to do this research in Wisconsin, is there research elsewhere that shows how PFAS affects aquatic life?
Yeah, I hate to admit it, but Wisconsin is a little behind. There's other states and also academic researchers that have been doing this for a while. Like, for example, let's say, California has been doing PFAS research, not only within the state, but other areas as well, like academia. Also, some of the eastern states, are just like across the border. Michigan has been doing a lot of work as well. Minnesota has a lot of good work too. There's a 3M site in the Twin Cities area that they're working with right now, and they're using going to be using some technologies to actually what I'm talking about, remove it, concentrate, and destroy it. So they have a pilot plant working there. There's been some other areas of the state of the country that are doing this quite regularly. We're basically getting up to speed. Although, like, some of these areas, no one's ever done a vertical profile of PFAS that I know of.
Good. So Wisconsin's still cutting edge for some things. That's good to know.
Yeah. But I mean, no one's got, in 2019, no one knew what was out there. So we're starting to, it's nice to know what people are doing in other parts of the country, but you need to know some of these things may be particular to your environment, your backyard, and certain water chemistry parameters or environmental characteristic or fish assemblages in your lake or your area. So you may have to study your specific area. So we're getting a handle on Wisconsin.
Great. Let's see. We have a volunteer that asked a question about monitoring in areas of high PFAS concentrations. Is that something that volunteers should be concerned about? Can you get affected by PFAS through touching the water through your skin, or should volunteers wear long waders, or what are the concerns there?
Well, I think just in general, well, obviously you don't want to be drinking surface water. When talking about a contaminant, you got to look at risk and routes of exposure to evaluate those risks. Obviously, you don't want to drink it if it's high in level. There's, from my understanding, what I've heard from DHS is that there's not really good evidence that it'll, permeate your skin, or it can go through your skin very well. But then again, if you wear gloves, that will take that away. So if you wear gloves, if you wear waders, I think you would be fine. So just minimum, those types of protection would be totally adequate.
Thank you for that. One of our volunteers is noticing that some levels for fish in Lake Monona are over 140,000 parts per trillion. Is that a don't eat advisory? So what is the don't eat advisory set at?
Well, I could go back to that graph. Oh shit, I'm having a mental. Is it 200? That level seems. I'd have to look at the level. Could you repeat that level? Something thousands?
140,000 parts per trillion.
I'd have to look at that to see if parts per trillion, because I'm familiar with nanograms per gram. If that's 140 nanograms per gram, that would be the in between. I'd have to show you where that is on the graph. I think 200 is do not eat nanograms per gram. I'm sorry, putting me on the spot. I'm having a mental fart of going in between the nanograms per gram. I think that might be 140 nanograms per gram on my graph. So that wouldn't quite reach 200.
Okay, and then we still have several. We
Sorry.
still have several questions left. I just want to let people know that we are officially ending our or the official end time for our presentation is 1 o'clock. But Pat, do you mind staying on a couple extra minutes to answer a couple extra questions, or do you have to run?
No, I got yeah, I'm pretty much free till 2 o'clock.
Okay, all right. So if folks need to leave, that's totally fine, but we're going to keep asking a couple questions here. It looks like we have 3 questions left. So our next question is, do traditional activated carbon filters found in refrigerators or water pitchers filter out some or all PFAS compounds?
I believe that they do. Theoretically, I think they do. I'm not up on the exact filters, or let's say I'm assuming this is like a Brita filter. I believe that they do, just generally active, in general, activated carbon does remove organic compounds. PFAS would be one of those.
All right. Is wastewater biosolids on land a problem?
That is an active area of research. Waste biosolids can contain PFAS. That's something that I know the DNR is actively looking at. We don't have any standards for those. There's, like I said, we're looking, we're a little behind other states looking at, let's say, like Michigan. I know Maine's done some work on that. So we're definitely looking into that because it could be.
Okay. And then the last question that we have here is that Starkweather Creek is contaminated from likely the Dane County Airport. Are there other airports with drainage runoff creeks being monitored?
One of the creeks I showed you was Silver Creek, which is up by Fort McCoy. That's another one that they used AFFF at that fort. I believe that was a airport area. So that's how that got in. Another example of where this caused a problem, I didn't mention it, was French Island. If you're familiar with lacrosse, basically there's lacrosse that's, on land, but also French Island, which is somewhat surrounded by the Mississippi River. There's an airport on French Island. There were burn pits, and there was a plane that caught on fire there. So there were areas that AFFF was used there. There's some groundwater contamination due to the use of AFFF at that airport as well. So those are all areas that that are being looked at and measured.
Okay, we had a couple other questions come in.
Oh,
All
wow,
right.
they're starting to fly in now.
Yeah, they are. This is an interesting topic, Pat. There's lots to talk about here.
Okay. How do you report?
Yeah, you see that one? How do you report private well results?
How does that mean? How do I personally, or did somebody want to know how they should? How do you report private well results or lake results to the DNR? I'll answer that from the perspective of me. When we take samples, we send them to the State Lab of Hygiene. For the most part, those samples, when they get reported to us, they go into the SWIMS database. I think most of you should be familiar with the SWIMS, so they're in that database. So that's that's how we operate that. That's how we get the results. I've been working to get them on that surface water or on that PFAS viewer, specifically for PFAS. Well results. If you have I used to work at the State Lab of Hygiene, so I could tell you this. If you have your well water tested at the State Lab of Hygiene, they will go into that database is shared with the DNR and you. So when you get your results, it'll go into the DNR database. I don't know if that's what you're asking. I assume if you do PFAS, it would be the same, but if you do nitrates, some sort of coliform bacteria as well. Maybe that's more than you want to know.
Yeah,
are PFAS in fish stored in fatty tissues? No, it's the meat. They're considered proteinophilic. So similar, let's say like mercury, they're bound to the meat. So it's the piece that you would eat. It's not like PCBs or some others where like an organic contaminant where you can scrape off the fat and get rid of the organic bound to the fat. So yeah, so it would be in the meat of the fillet. So that's why it's important. Thanks for that. I'm not quite sure. Okay. Okay, I got a shout out. I have, okay, Friends to Starkweather Creek. I have given a talk to the Dane County Board, just FYI, basically showing them the results of what we've been finding in Lake Monona and so forth. So that was not the full board, that was just the Land and Water Conservation, or Land and Water Commission. Sorry if I misspoke that. But yeah, sure, thanks. Thanks. I'll try to get in touch. I asked the question, if you use a private lab, how do you get it reported? Oh, this person wants it to get reported to a private lab. I believe, I'm not sure how private labs work. I don't know if that's shared with the DNR or not. Is that what this person's asking?
Yep, I think that's
Gwen?
what she's asking, yeah.
So I'm not sure. Oops, I just jumped to the question and I lost your question. Okay, yes, that's the question. Should just unmute people. I don't know. You might have to ask the DNR, sorry. Or ask the lab, I'm sorry, you might have to ask the lab how, if they report it to the DNR, you might have to do that yourself. I don't know if they share the databases or not. Hopefully that answers that.
Yeah, and I'm getting a lot of little private messages too, saying that was a great talk. We see when Lisa came in and said, excellent talk, great info. And I agree, it was a really interesting talk, and we are recording today's talk, so we will send out a link to the recording after the presentation is over here today, once we get everything uploaded. And just want to say thanks again to Patrick Gorski for joining us for our winter water talks. Our next one is on March 15th, and we'll be talking about wetlands. So stay tuned to your emails for registration about that. And we hope you join us next time. So thanks again, Pat. We'll see you.